19. Rotation in Euclidean space. We know how to rotate a vector in 2 dimensions, and it is simply multiplying this 2 by 2 matrix. If you forgot everything, don't worry. Just remember angle theta, sector. Just remember how this point transforms under rotation. Under rotation, it transforms into this point. So 1, 0 vector transforms into where? Cosine, sine. Okay? Therefore, if you have a matrix, if you multiply 1, 0, your answer should be cosine and sine. The answer is just copy this result like that. And then you rotate 0, 1. It rotates to this point, and it is a right angle, and cosine and sine are flipped. Remember, this is on the left side. You have to put the negative sign on it. So if you multiply 0, 1, your answer should be this, that is a minus sine cosine. So you copy this one in the second column. And as a result, you can recover this 2 by 2 rotation matrix. In mathematics class, you usually learn passive transformation. Passive transformation says you keep a vector invariant, and mathematics class just to rotate the axis only. It is frozen. Mathematics doesn't want to touch the world. Physics likes to touch the world. I mean, if you play a baseball, a bat hits the ball and fly, and you want to see whether it's a home run or not. That's physics. Mathematics is frozen. They don't want to change anything. Keep this point as it is and want to change the viewpoint. This is mathematics. This is physics. We are interested in the change of the space, change of matter. So this kind of transformation is active transformation that changes the vector itself. This kind of transformation is nothing but the change of basis to a fixed object that does not change. So we say this mathematical approach is a passive transformation. Physics likes active transformation. They are exactly the same except that there is a negative sign. In mathematics textbook, you will mainly learn negative sign here. But in physics, we don't like this. I like cosine sine because I want to transform a vector. You have to remember it very carefully, and you need to think. Okay. And mathematics textbook always says you need to remember what the matrix is, and you need to remember the rule. Physicists control the rule. Why? We know the origin. Matrix is just the result of a scalar product. And this scalar product becomes very simple if you like Descartes. They usually do not say what Descartes has done, and Descartes' best work is to decompose a vector into Cartesian unit vectors. And these are Cartesian components, and Cartesian is the adjective of Descartes. You need to remember. If you remember Descartes' face, then as soon as you see scalar product, you are able to reproduce the scalar product is simply expressed as a sum of products, and sum of products can be easily expressed as a product of row vector and column vector. Remember, Descartes did not learn about matrix. Descartes created matrix. That's simple. Then don't worry. If you want to multiply any matrix between them, this is a simple rule. It is too busy to write this one. Just separate them into two pieces as a row and column and multiply them in order. First, second, third, and then add them all. Origin of this matrix product is nothing but the scalar product in terms of Descartes' notation that is called the Cartesian coordinate. This is true only for the case EI dot EJ is a Kronecker delta, and that Kronecker delta is the ij element of this simple matrix that is identity matrix, and every off-diagonal term elements vanishes, only the diagonal elements is exactly one. These two are equivalent. In general, I can insert any 3 by 3 matrix because B1, B2, B2, B3 can be multiplied to these 3 rows, and then after multiplication, it becomes a single column, and then it is to be multiplied to this row. In that case, we end up with a single scalar that is a number, single number. However, this complication is greatly simplified if we work on this basis, because only 1, 1, 2, 2, 3, 3 survives, and E1 dot E2, these are different indices. As soon as they meet as a scalar product, it is a 0. Therefore, the scalar product is simply expressed in this way, and even I can delete this. Okay, so we'd like to know how a vector transforms under the multiplication of this rotation matrix. This is the original Cartesian components. I'd like to multiply this to the left side, and my result is first A1 cosine, second A2 minus sine, A1 sine, A2 cosine, A3 survives only in the last element. Show that rotation matrix inverse is nothing but the transpose. We remember exchanging a row into a column, and the column into a row is called transpose. If I write this one, rotation matrix, transpose means copy this row into column. Copy this second row as a second column. That's it. You can see cosine is an even function, so I put negative sign on it. I still have the same value. They are diagonal elements are invariant. Sine is an odd function. If I substitute minus sign over negative sign survives, so it is an odd function. Therefore, it is nothing but transpose of a rotation matrix of angle theta is exactly the same as the rotation matrix with negative theta. In addition, if I rotate in this way and return to the same point, what's that? This is rotation by plus theta. Returning process is rotation by negative theta. Therefore, I find that the inverse is the same. This inverse, r theta's inverse is r minus theta, and r theta's transpose is r minus theta. So they are equivalent. So in many cases, if you learn mathematics, it is a very awkward to compute the inverse matrix. But if you are doing physics very well, then you don't have to worry too much about it. Most matrices whose inverse is just transpose. Remember, not always, but if you are working on a rotation matrix, or usually it is this kind of matrix is called orthogonal in a mathematical word. In physics, it is very simple to say rotation. What you have done with the rotation is just to rotate the unit vectors. What happens if you rotate these unit vectors? They used to satisfy ei dot ej equals delta ij. What happens if I rotate everything all together with the same axis with the same angle? It is not complicated. Scalar product is invariant under rotation, and at the end of the day, after the rotation, whatever value components it may be, your answer is still the same. Because of that, any rotation matrix consists of columns or rows. They are all satisfying this simple relation, thanks to Descartes. Okay? So because of that, any column's scalar product is just a delta ij. Let's see. Square of this cosine sine square equals 1. Okay. Sine cosine square 1. Okay. This square is 1. Everything is okay. And what about the scalar product between the two columns? Cosine sine minus sine cosine 0. Simple. Any scalar product of two different columns or rows, they disappear. Only itself square is 1. Very simple. That's the reason why rotation matrix inverse is nothing but the transpose. It is very, very stupid to compute the determinant and adjugate to find the inverse. It's trivial. Just exchange these two. That's the inverse. You need to know this story. Okay. As soon as I tell you that computing determinant is stupid, but let me be stupid again. Determinant r theta is what? The answer is 1. Let's see, determinant is what? Determinant of a 3 by 3 matrix is A1, A2, A3, B1, B2, B3, C1, C2, C3. I like Descartes. It is a very busy way to write a determinant, but according to Descartes, it's nothing but the scalar product of the three things. And we know, thanks to Descartes, we know EI, EJ, cross product, the scalar product. What's that? It's nothing but the Levi-Civita tensor that is a epsilon ijk. It looks complicated. However, epsilon 1, 2, 3, 2, 3, 1, 3, 1, 2, they are all even permutation. They are 1. And if I exchange any two of them, the sign flips to negative sign. Exchange of these two comes from the anti-commutative relation of a scalar of the vector product. A cross B equals minus B cross A. Because of this one becomes a 2, 1, 3, 3, 2, 1, 1, 3, 2. They are all minus 1. And we have 3 elements to list. 3 factorial, that means 6 cases. Among 6 cases, we have 3 even permutations and 3 odd permutations. Even permutation have positive sign, odd permutation has negative sign. So applying everything all together, determinant of this matrix, this is even simple. C S minus S. Determinant, choose one thing, choose next thing, choose one thing, choose the next thing, different column, different row. However, this is rotation matrix first element first. This is second row, second element. This is first row, first element, second element. This is a second row. This is second row, second element. No, first element. Minus sine, sine, cosine, cosine. However, 1, 2, 1, 2, that's fine. However, this guy, epsilon 1, 2, this guy gives epsilon 2, 1. I need to multiply epsilon 1, 2 plus epsilon 2, 1. Epsilon 1, 2 is an even permutation plus 1. Epsilon 2, 1 is I have exchanged these two. I need to put the negative sign on it. So it is a minus 1. Substitute cosine, cosine, minus sine, sine. The answer is cosine squared plus sine squared. What's that? Middle school students know that it is 1. Determinant of R is 1. It's not the end of the game. This is a very important because what I like to do is I like to carry out an integration over space. Integration over space of function. I'd like to change the coordinate system to x to x prime. And x prime can be expressed as R product of x. Here I say it is a x1, x2, x3 as a column vector. This integral can be converted by changing the variables into prime variable, but it is not exactly the same. What should I do? There is an overall factor because I need to consider the transformation of components according to the rotation matrix. That is nothing but this. that is called Jacobian. Jacobian is what? Jacobian is a triple scalar product in the 3×3 cases, because dx cube integral is actually Cartesian coordinate x1, x2, and x3 integral. However, this can be expressed as a cross product and scalar product, triple scalar product. dx1 vector cross the dx2 vectors dot dx3 vector. This volume is to be transformed into x1 vector prime cross x2 vector prime dot x3 vector prime. And in here, we have a linear transformation because we have a x prime 1, 2, 3 are correlated with x 1, 2, 3 as it is. For example, x1 prime equals x1 cosine minus x2 sine, something like that. What should I do if I want to compute the dx prime? What I need to do is find the differential. Okay? Oh, they are mixed. What I want to do is x1 prime, x2 prime, x3 prime. But if I substitute this one, what I get is dx1 cosine minus dx2 sine. And then the next one will give the dx1 sine plus dx2 cosine, finally dx3. I need to expand everything all together. But simple way to compute this volume is nothing but the determinant. Why? Why? A cross B dot C is the volume of a parallel pipe spanned by 3 side vectors A, B, and C. That is why. Why? What you have done is the determinant already. Therefore, as you can see in here, volume after rotation can be expressed as a triple scalar product, and eventually they are expressed as the determinant of the rotation matrix. That's the reason why we learn Jacobian, and Jacobian can always be computed with a triple scalar product. In case you are working on multivariable cases, it is simple to generalize this. Once you know how to compute epsilon ij, then you can simply compute epsilon ijk, and then 4×4 case ijkl. It is easy to generalize this with mathematical induction. So, in summary, after rotation, because the determinant of the rotational matrix is always 1, you don't have to worry about the Jacobian. Okay? You worry too much about it, but because it is 1, you can remove Jacobian because it is exactly 1. So simply any integration can be done without any additional factor. But in general, you have to check whether it is really 1 or not.